So welcome to this lecture 6 already on privacy protecting natural language processing. And well, I put in the title local DP and randomized response, so we'll get to that. But let's first recap what we have been doing so far. So I really want everybody, to kind of keep track where we are heading. So to keep the red line, why is it important, and not just showing things and mathematics and just okay, this is it and learn it. So what we covered so far is if we want to do anything formally, like prove something, probably private data analysis, whatever it is. So we were, the counting queries and stuff like that. We need some randomized algorithms. So randomization is the key for keeping privacy because you cannot undo it. So then that's it. You can privatize things. We had this notion of so-called central differential privacy and also pure differential privacy. Okay, so what does it mean, the pure? So we are mostly talking about the epsilon. So what's the epsilon again? How we call that? The epsilon? It's a privacy budget, exactly. We still don't know why it's a budget. I mean, we kind of know why it's a budget, but we will know, you can split it and then that's why it's budget. And once you run out of your budget, I'm sorry. So this is the privacy budget, and this 0 here is still a bit formal, but I guess in the next lecture or maybe in 2 lectures, we'll come to something which is not pure differential privacy. But so far we have just one parameter epsilon. And why is it called central? Well, we have this trusted curator. So if my colleague would be here today, that one, who knows how many of you, what was the question, cheated in exams or something? Yes, so he will be the trusted curator, and that's the person who you trust. Okay, so this is the central. So there's a database. The hospital has a database of patients and things like that. Somebody who trusts. And we also talk about a couple of mechanisms, mechanisms and queries and some properties. So the most, I wouldn't say simple one, it's not simple in any case, but it's just the basic mechanism is the Laplace mechanism, where we are drawing numbers from the Laplace distribution for numeric queries. And these were, as we saw, either reporting one number or it could be a vector of numbers. So the Laplace mechanism works for reporting vectors as well. And we had this notion of L1 sensitivity. So this is the maximum difference one person can have on the output of the query. So if you remove one person from the data set, it will change by some maximum. And we also talk about the exponential mechanism, where actually we kind of forget about these numeric queries and took like any range queries. So anything, any output could be arbitrary sets. And we had this example, what was that? The secret society meeting of the cities. So we could have actually modeled this one with the Laplace mechanism, because at the end of the day, in our cities, we had the GPS coordinates, and we could measure, basically, we could randomly sample coordinates. Well, not randomly. We could kind of have a medium coordinate and then just sample from Laplace distribution on 2 dimensions and get somewhere and just take the closest city. But we use the exponential mechanism just to showcase, you can have arbitrary cities, and we have the utility function and sensitivity. So this is the recap of so far. We haven't talked about NLP much, but as we discussed after the lecture last time, the exponential mechanism could be useful for it's similar actually to sampling from softmax with temperature, and it could be then used in sampling from a language model. And we will see later that it is actually used in sampling from language model with probable guarantees. But we need one step in between to understand a little bit different setup. And the little bit different setup is that we had a trusted curator. Yeah, nice. But what if we don't? What if we don't have a trusted curator? You were the trusted, no, the other person, but not today. You're the trusted curator, okay? You have no business today, so there is no trusted curator. Well, that would be great, right? I mean, if there is nobody and you have to trust, but you can only trust yourself, this is the best thing of privacy, like you only know your stuff and no one else knows that. That's great. And that's what we're gonna be working on today. So moving from this, central database, and I give my data to somebody, and then somebody will take care of privatizing any queries coming onto the database. I'm just going to do myself. It comes with a cost. But anyway, yeah, so mathematics refresher. I mean, this is, I hope the level of math is okay for everybody so far. I mean, we had this exercise last Friday where we kind of were typing, the proof of Laplace mechanism online. It was fun for me, actually. So I kind of enjoy like typing LaTeX live. It shouldn't be any harder than we had so far. So if you're fine with all these kind of things, then I believe it won't be any more brutal. But we need to just refresh something which I guess everybody is supposed to know from probability theory, but just to make sure that we are on the same page. So it's the Bernoulli trial or Bernoulli distribution or Bernoulli random variable or indicator random variable or whatever. It's the simplest kind of probability distribution, I would say. Because let's say we have a random experiment that succeeds with probability theta and fails with probability, the remaining probability is 1 minus theta. Okay, so we have two outputs, success or failure, which we typically model as 1 and 0. But this is just an arbitrary choice. So it's like how you map it, it's your choice. What matters is not the success and failure, it's the 1 and 0. Okay, so these are the only outputs of this random variable. So it has the image of this function is 1 and 0 as a set. So the k is either 1 or 0. So then this random variable has the probability distribution on k. So y equals 1 is theta. So this, of course, I mean, this is probability of the success, and 1 minus theta is probability failure. Okay, so no surprise here. Okay, let's say we have a coin. So what's the theta for a coin? So it's throwing a coin. Toss a coin. What's theta for coin? So we have a coin like heads and tails. You can say okay, heads is 1 and tails is 0, or the other way around. It's up to you to decide. What is the theta? What is the, yeah? It's a half. It should be half, 50-50. So exactly. If the coin would be biased, then it's not 50-50. So there's another example of this Bernoulli trial not with a coin, because it's so well known, and it's 50-50, and it might be misleading in some cases as an example. There's another one with throwing, and I forgot his name for that. If you pin something on the wall with this thing, so a dart. Well, it's not a dart. It's like an office supply. So you have a poster, and you kind of, if you have a poster on the wall, how's it called? Oh, a thuck? Well, something like that. I don't know. The tag? Tag, yeah. So it has this kind of sharp edge, or sharp, what is this? Oh, Jesus Christ. Okay, so I'm out of my terminology in English, or in any language. I just completely forgot how this thing is called. But anyway, if you toss it, well, it will fail either, on the head with the edge up, with the sharp dot up, or the other way around. And it's not 50-50, I guess. Right? So most of the time it will fail. I don't know how exactly. Maybe it's 50-50, but I don't think it's 50-50 because of the dynamics and the and the mass and stuff like that. So it could be an example. Okay, but coin tossing is one example. Okay, so we can express this as also as just a single line expression, which if you replace k with 0 and 1, you get one of those things. And this is kind of, well, maybe we'll need it. I mean, this is kind of showing also that Bernoulli trial is a edge case for a binomial distribution. So if you remember, if binomial distribution, number of how many successes you had in a number of trials. If you limit the number of trials to 1, you get just one Bernoulli trial. Okay, but we don't need binomial today. So just Bernoulli trial. Okay, one parameter theta, the probability of success or probability of 1. Okay, makes sense? Everybody's happy. Cool. That's it for today. So our question was, what if we don't trust anymore? Okay. And I'm gonna take a little bit different approach from what I've seen people doing. We're gonna explore this and try to, yeah, we're gonna design it by our own, like how to do differential privacy from zero, a local differential privacy. So what do we need to look into in differential privacy now for the local one, or well, in general, we have this notion of neighboring data sets. Okay, so what was the notion of neighboring data sets? So we had neighboring data sets of size n, and then we removed one person, and we had data set of n-1 was the size. And we call them d and d prime, something like that. But I also said, as far as I remember, that we might have another notion of neighboring data sets, and this is just if they differ in one row, so which means one row is replaced. So we would have the same number here, n, same number here, n, but one row will be different, in those databases. So this is also the neighboring data sets. And so far, we use this kind of one person minus one person plus, and everything works so far because the sensitivity, for example, for counting query was the amount of one person which can kind of contribute to this query. It will be the same basically for this one as well, for the neighboring data sets where they differ by one person. Because if you have, for example, even like counting query, so here this would be 0, and here this would be 1 for the kind of private bit. Yeah, then if you replace one person with another, the same sensitivity kind of works. So basically all these mechanisms we talked so far about, like the Laplace mechanism, would be the same even for this notion of these databases. It will be different for one example, which is the histogram query. And maybe we should make a little bit detour here, because we didn't talk about histogram queries, so maybe it's important to mention. So histogram query. What is a histogram query? So what is a histogram? Some counts for some bins. So you have a data set, and you kind of distribute it among some properties. So for example, if you have persons by age, so you might make it a histogram. Okay, people younger than 20 years, 20 to 40, 40 to 60, and 60 plus, for example. This could be one example of a histogram, and then for each of those, you would basically count the number of people in your database. Okay, makes sense? Cool. Then, and so before we say like how to privatize this histogram query, so if I ask you, okay, you have a hospital today, okay? So you're a hospital kind of director, and I'm going to ask you, okay, we have 4 different groups. I need a histogram. Will you give me a histogram? And if you just give me a histogram, we already know that, if you give me just the raw data without privatization, privacy and blah, blah, blah. So it's not good. The first question is like, what is the sensitivity of the query what are the neighboring data sets? First, if you take neighboring data sets by removing one person, what is the sensitivity of the histogram query? Okay, so histogram query means I have 4 categories, and for each of them I report the counts. How many people are in this category? So what is the sensitivity, L1 sensitivity of the query if I remove one person from the database? No, if I remove, so let's say I have in each of the category, I have 2 persons, okay? I have 2 persons under 20, 2 persons 20 to 40, 2 persons 40 to 60, and 2 persons 60 plus. Okay, so, and I'm gonna report this to you. So it will be like a vector 2, 2, 2, 2. Okay, what if I remove one person from the database? What happens? It will be either, if the person is until 20, it will be like 1, 2, 2, 2, or 2, 1, 2, 2, and so on, which means the maximum difference between the queries, L1 norm, will be 1. Because if I remove one data set, I'll remove this person from one of those bins, okay? This is 1. Now, what happens if I use this notion of neighboring data sets, which means I replace one person? So what might happen is something different. The sensitivity will be different. And why is it so? Because now I the person might change group, the bin. So it might be person, like I remove one person or I replace one person from 20 until 20 years with another person, maybe 20 to 40, which means my response will be 1, here will be 3, and 2, 2, right? Because I decrease a number in one of the bins and increase the number in the other bin because I just replace the person with somebody who is fitting in some of the other bins of the histogram. So what's going to be the sensitivity right now? So if I change a person, I can change from 2, 2, 2, 2 to 1, 3, 2, 2. What is the sensitivity? It's going to be 2, exactly. So sensitivity of the histogram query will be 2 if I use the notion of neighboring data sets that I replace one person with another person and not remove the person from the data set. And in this case, you have like a factor 2 different sensitivity. And of course, then you can run Laplace mechanism on top of these numbers and report the privatized value, but you have to take into account like what the sensitivity of the query is, because if you screw up sensitivity in Laplace mechanism, you might screw up the complete privacy. So this is why histogram query is interesting in terms of what is actually neighboring data sets. Okay? Does it make sense? I didn't have a slide on that, but I thought like I should mention that because this is one of those examples where this actually matters. Where this matters. Okay. So we talked about a histogram query, no slides, but I guess it was like a clear example. Now you might be asking, well, okay, what if the size of the data set is 1? I just want one person in my data set. Is it possible? Yeah, why not? It shouldn't be empty. Like empty data set is like kind of bad. So yeah, and it shouldn't be infinity because it doesn't exist like in real life. So it should be some finite number. Could be any finite number. It could be 1 also. So this is interesting. Can we have data set of size 1? Yeah, why not? There's only one patient in your hospital. Cool. What is their age? What is the average age? Yeah, exactly. So yeah, I don't know. I mean, whatever, but it could be a number. And you just make an average of one person. You can do that. There is nothing preventing you to have one person in the data set. So then we would use this notion of neighboring data sets. If we have just size 1, then you would obviously, if you remove 1, then there is nothing and that everything will break. So you will have to have a notion of the neighboring data sets of just one person and maybe another person. Okay, makes sense? I mean, we can have database of size 1. And then, can we ask numeric queries on database of size 1? Yeah, we just did. Like, I'm going to ask you what's the average age? And you're going to say, well, okay, there's only one person. Their age is 30. What is the sensitivity? Well, you have to know the sensitivity. So it will be maybe 130 because this is the minimum and maximum age in your domain. And you run a Laplace mechanism and give me the answer. Good. So it will work. Nothing will change from the bigger database to database of size 1. Agree? Yeah, this is great. Or here the example. Okay, this is maybe, well, okay, before going there, I mean, now we take a step in thinking. So instead of you're what was that, a director of the hospital, you're just you, and you have a database of size 1, which is your secret thing. Okay. And now the example query could be like, what's your average age? Yeah, so you can basically do the same thing as before. You take your true value, run a Laplace mechanism, and report me the value back. There is just one person in the database, and it's you. And I might know it. I might know it, but if you report me the privatized mechanism, I don't know what's your exact age. I just know something like, yeah, maybe something around. Well, you draw it from Laplace, which was around your actual value, but it will be somehow off. So there will be some error. So I don't reveal anything about your age. I have another example here. So now my query could be like, how many classes did you skip? Okay, so you're here. I mean, I should ask the other people who are not here. So how many, okay, people, how many, so these kind of people who are not sitting there. People, how many classes did you skip and instead like watch Netflix? And the answer will be something between 0 and maybe 15 because we have 15 classes. And again, you just need the Laplace mechanism of the, You just take the true answer, run the Laplace mechanism with the proper epsilon. I mean, epsilon, we have to agree on that. Okay, so which epsilon? I don't know. Let's take 1, for example. Why not? Is it good privacy or not? It really depends. But let's say it's good privacy. So you give me the answer and I'll be happy. But so this is, you see the step from like, well, database of size 1 and your own kind of personal database, you can use the same mechanism for reporting the query on top of that. But what we just did is that by, two things maybe. So the first one, let me start here. By privatizing the raw values shown previously, it removes the need for a trusted curator. So because what I'm interested in actually is not how many hours how many lectures you skipped for, watching Netflix. I'm interested on average. Like how many students are actually not coming to the lectures because I don't know, it's nice weather, or no, they actually do something more kind of, more fun, watching Netflix. Or maybe something even harder, like how many of you actually are going to cheat in the exam on average? And this is what I'm interested in. I'm interested in some statistics, average number of lectures skipped across all students, or I'm not interested in I'm not actually interested in your answer or your answer or your answer. I want to do some statistics, like how many people are actually cheating in exams. I think we have an example on cheating exams later on, but it's a good one. So we know, I mean, this step we did here is that now you don't need a trusted curator. I can ask each and every one of you the same query, and I'll get some answer which you privatize from your data set of size 1 using a known mechanism. And then I collect all these answers, and maybe I can, with some error, reconstruct the true underlying value. And let's make this even simple, like not a true value between 0 and 15. Let's make it even a bit. So just reporting single bit. Okay, so did you cheat in the exam? So you took the last exam in winter. Okay, so let's pretend you took my last exam in winter, and I'm really interested in how many people cheated, because the grades were actually pretty good. I mean, I was surprised. So maybe I don't know why. Maybe people learned, they pay attention, or maybe the previous exam really leaked in a way from somewhere. It's possible because we have internet and stuff like that. Or maybe they cheated because they have all these kind of cheats somewhere written, and I'm really curious. So what I'm gonna do, I'm gonna ask you, did you cheat in my exam? Yes or no? Okay, did you cheat in my exam? Did you cheat in my exam? Are you sure you're gonna tell me this? Are you really sure? No, you didn't. Did you cheat in my exam? You? Yeah, okay. So here's the thing. I mean, if I'm gonna ask you, your answer will be no. Of course, never. But so yeah, that's bad. So can we somehow fix that? Can we use this notion of local differential privacy so that you privatize your answer before reporting in such a way that your privacy will be protected? Because we know that with randomized kind of mechanisms, you protect privacy of people in your database. Even this is you and the database is size 1. We know that. And at the same time, if I collect the answers from all the population, or the more the population, the better estimate I get of the underlying kind of value. So for example, the percentage of people who actually cheated. Okay, so this is what we're trying to achieve today. But just once again, we're coming from the trusted curator database of size more people to just size one person. But everything else should hold, like the neighboring data sets. Yeah, they just differ by one person. What does it mean? Well, if we are in the single bit, so what could be the neighboring data sets? So neighboring data sets D is a single bit, for example, 0. D prime 1. Yeah, sure. Yeah. This is the maximum difference you can have in two data sets of size 1, each of them having a single bit. Okay, good. And so this is the notion of the, this is it. This is just a single row and single bit, and they differ in one person, and the maximum difference could be, well, if they're both zeros, well, okay, that's possible. And if they're 0 and 1, this is the maximum difference. So this is the neighboring data sets. Okay, good. So let's say that each person has a secret bit. For example, like I took illegal drugs, or I cheated in the exam in the winter term, or stuff like that. So, and my query I'm interested in is like what percentage of students took illegal drugs. Not whether you or you or you. I mean, you will. Come on, you will never tell me that you cheated, because there's there could be bad consequences if you did. But I'm actually thinking about it. I'm really curious, why the grades were so good.
The exam was actually quite easy.
Was it easy? Okay. No, this is a genuine answer. Okay, so yeah, it was easy. So you'd be surprised, like, because as I said, okay, so this should be off record. So I've been using that, like, a couple of times, as I told you. So that's why I didn't give you the exam before. And you scored like much higher than the other people, like in some other university where I gave this. So I don't know, but I hope it wasn't cheating. Okay, cool. Maybe you use the exam. Maybe you learn, and that's why it was easy. I think, like, if you learn something, then it's getting easier. You just.
We had a class on AI the semester before, human-centered AI.
Yeah, but not everybody.
Yeah, but I think quite a lot of people that take AI classes with the other before.
Okay, cool.
People are only allowed to choose those lectures if they already passed the math lectures. So they needed.
So there was a filter. Yeah, but okay, there was a filter, but there was not. I mean, we didn't actually do any math in there. Like, it was more.
People are treated. They know they need to learn.
I see.
So,
okay, yeah. So this is it's a filter in a different way. Anyway, okay. So reporting single bit neighboring data set 0 and 1. Okay. Cool. So how to do this? So now we have two extremes. So from the true value. So for example, let's pretend you cheated. I'm sorry. Okay. So let's pretend you really cheated, and you wanna. I'm gonna ask you, and you're gonna tell me the reported value. So we have two extremes. Just report the truth, right? It can't be any worse. So there is no privacy, and answer completely randomly. So this is a toss coin. So you just say like, yeah. And I know you're answering randomly. Okay, so there is no obscurity, security by obscurity. This is public information how you answer. So either you say, I'm telling you the truth, and by the way, I cheated. Happy, good for me. I'm happy because I have like no noise in the data set I'm collecting from all of you, but bad for you because you have zero privacy. And the other one is, if everybody answers completely randomly, what I'm getting, like, if I collecting like 100 answers from people just randomly tossing a coin and saying yes or no depending on coin, I'm gonna get like, yeah, 50% cheated, but it's completely random. Well, I didn't have to ask in the first place. So what we need is something between these two extremes. Okay, that would be great. So something between complete privacy and complete useless utility, and 100% utility and zero privacy. As usual, this is the trade-off, utility privacy. So how to report a single bit? Okay. So the idea is that we report the true value with some probability, will be the true, or flip the value. So the opposite, if you cheated, you will tell me I didn't cheat with, with 1 minus some probability. Okay. So there will be some randomness. How exactly does it mean? So what the algorithm should be doing? How to do it both, with some probability exactly. So we use a randomized algorithm. And again, so it could be 2 steps. First step would be a draw random value, either 0 or 1, from a Bernoulli distribution. Okay, now we remember what Bernoulli distribution, Toenkosing, or this tag thing throwing, or I don't know, something, some random number generator in NumPy. So you draw a random value, either 0 or 1. And then in second step, so if you drew 1, you tell me the truth, the true value. And if you report 0, you tell me the opposite of the truth. Okay. Sounds like it's gonna do something. Correct? I mean, there is some randomness in this process, and you know exactly how the process looks. So we can use this algorithm. Now, the cool questions to ask is like, what the heck is going to, you know, how the privacy is going to work out in this case, and what exactly should be the Bernoulli distribution doing? And the second, like, well, is it any good? We'll start with the privacy one, okay? And again, so 1 is usually associated with true or success. Well, we discussed it before. But again, so we have an algorithm. We know roughly how to do that. So there should be some randomness, and the randomness should be, well, should be non-deterministic, obviously, as randomness should be. But the true answer should depend, sorry, the reported answer should depend on the true answer to some extent. It shouldn't be completely random, because these were one of those extremes. So we need to be somewhere in between. So everybody's happy with this algorithm. You know, you choose 0 or 1 randomly, and then depending on this outcome, you will tell me either the truth or the opposite. So the first question, how to parameterize this Bernoulli distribution, right? We have this parameter theta. So what theta would we need for modeling the extremes? Okay, let's start with the extremes, maybe, you know, the worst case and the best case, and then we know where the theta should be in between. So, and also the theta is publicly known, by the way, okay? So this is everything is public except for what was the random toss. Everything else is public information. So no security through obscurity, exactly. So extreme 1 was just reporting the true value. So what is the, without looking into the slides, what is the theta for reporting the true value? So look at this algorithm again. Draw a random value, either 0 or 1 from Bernoulli distribution. So now we know what is Bernoulli distribution. And if we got 1, report true value. So, and if we want this extreme, like always report a true value, what's the theta going to be? Say again? Okay, this is one option, 0. Any other opinion? I tell you why it's not 0. So if you have a 0 in Bernoulli, then you will always get 0. Okay, so let's do this again. So if theta is 0, so this will be 0, and this will be y minus 0 is 1. So you will be always getting 0. Make sense? So it's not 0. Anything else? Because 0, if I get 0, I report a flip value, not the truth. Well, actually, it's bad. So actually, this is bad because it could be 0 because, well, okay, you're right. It might be 0. I would first say it's 1. I mean, with theta 1, I would always report the true. If theta is 0, I would always report the opposite of truth. So that's also bad. Okay, so both of them are correct. So thanks for that. Yeah, so we double check that. Okay, so report the true value with Bernoulli 1 and always returns 1. So always true, no privacy. Yeah. So the second extreme, what would be the completely random answer? What theta we need? A half, exactly. Why? They're both possible, and the answer actually is not depending on the truth, because it's just either or not. So no matter what the raw value is, this is equivalent to reporting a random value. Okay. Okay, good. So now we know that our algorithm has to be parameterized by Bernoulli's, so excuse me, by the Bernoulli algorithm, or the Bernoulli distribution in our algorithm has to be parameterized with theta between 0.5 and 1. Agree? So if this is below 0.5, then we are leaking some information already. So it has to be 0.5 is completely random, 1 is completely truth. Well, okay, we could have done it from 0 to 0.5, but this is equivalent basically, and maybe it's nicer in this case. Okay, so between these two values. Good. So how to parameterize this? Let's think like a large language models. Let's think step by step. Okay. Do you know this prompting of LLMs? Let's think. If you ask ChatGPT and say like, okay, let's think step by step, it's trying to think step by step. Although it's really interesting kind of type of prompting. Anyway, so let's play a LLM and let's try to think step by step. We're actually gonna really develop this thing from kind of our intuition and what we need, and we'll end up at something which is famous. If this approach doesn't work, then we can just backtrack from the well-known things and just do standard theory improved stuff like that. But I'm really trying to do it like bottom up. Okay, so we saw that the theta controls the privacy strength, right? I mean, the theta between 0.5 and 1 gives you something about privacy. Well, this is completely private and this is completely non-private. So we need something in between. Okay, cool. Yeah, great. So this is what we want. 0.5 more privacy, and if this goes to 1, it's less privacy. Now, if you remember, we had this privacy budget in differential privacy. So how to control privacy strength in differential privacy? So if you remember, epsilon is something between in range of 0 to infinity. And we had that epsilon going towards 0 is more privacy, and epsilon being 0 is actually complete privacy. And epsilon towards infinity or higher epsilons was less privacy. And it was like exponential kind of exponential strength of privacy. Okay, so now we need to find a function that maps epsilon, which is the strength of privacy in differential privacy, to how to actually parameterize our Bernoulli distribution in our algorithm, right? We want to build a differential private algorithm for reporting a single bit. Okay, so this is the task. And in differential privacy, well, I know epsilon, I can interpret epsilon, I know how to prove it. In our case, we have the Bernoulli trial with theta, something between 0.5 and 1. So how should we exactly set this so it kind of corresponds to these epsilon in differential privacy? This is the task we're trying to now kind of invent, right? We're inventing an algorithm from scratch. So we need this. Let me just see. Okay. So any idea? So we have epsilon between 0 and infinity. So this would be the epsilon. This is 0 and this is infinity somewhere. And we want theta to be between 0.5 and 1. So what could be the easiest solution to this? Like, what could be the function? So we need a function of epsilon that gives us theta. I was thinking like something, well, a line would be bad because line doesn't really go to 1 in the limit, like so it should have, it won't work. I mean, the only line that goes to 1 at infinity is just the constant function, right? So, but yeah, it's fine. It works for infinity, but it doesn't work for 0 because we need to have it here. So we need something else. We need something like, I don't know, something here, something here, maybe linear, and here something which saturates to 1, right? This would be somehow things. So yeah, what could that be? Trigonometric function. Yeah, okay, so some sort of trigonometric function, something which is smooth but then saturates to 1. I don't think like sinus, cosinus, maybe tangents, hyperbolicus thing. Oh, okay, maybe we're getting somewhere. Let's take it even simpler. Like let's make not the life complicated. So we want, again, this is what we want as a function of epsilon. And as I said, like the limit of 1 goes to 1. This is good. So does the limit, this is just the fraction goes to 1, and also limit s anything which you add in the fraction will basically come to 1. So this is good. And maybe this will give us some hint. Yeah, it doesn't work for epsilon because, you know, if you go to 0 with this function, epsilon over epsilon plus 1, it will be 0 at 0. So how to fix that? How to fix this, that if it's at 0, it goes to 0 to 1.5, 0.5. And I came up with an idea, just add 1. This is an easy fix, right? I mean, so let's add 1 here. And then if this goes to 0, we'll have 0.5, and if it goes to infinity, we have 1. Awesome. Everybody agrees? This is the easiest fix. I mean, this will, and maybe this will be the algorithm, right? And how does it look? I mean, I plotted the function. It's something really like that, some sort of knee. It goes like that, and somehow saturates to 1 if you go to plus infinite. Okay? Any other suggestions? I mean, this is like really the easiest fix. Sort of a linear function-ish way. Yeah?
So this requires epsilon to go towards infinity again. Like you will never need 1, right? You will only get infinity close.
So, okay, so what do you mean by that? Like, so epsilon will never be infinity. I mean, infinity is no number, so it will grow, and in a limit should be 1, right? And this is the same for differential privacy with epsilon. Like epsilon 0 differential privacy means the fraction. What does it mean? Well, we can have actually. Okay, wait a second. If we have infinite privacy budget. Oh, this is interesting. Okay, so let's try the definition. So the probability of the mechanism over D equals to some output is less than equal x of epsilon times the same mechanism on a neighboring data set for any y. So this is like pure DP definition. What happens if this goes to infinity? It means that we have an infinite privacy loss here. Yeah. So there's unbounded. So the ratio, so basically we plug this here down, and this will be unbounded, the ratio. So you will always find out the true value, like what's the database? Is it D or D prime? It will be always D or D prime. So this is like infinite privacy loss. So that's what you don't want. You want like a finite number. If it's infinity, then there's no privacy. And that's exactly what we have here. Okay, does it answer your kind of concerns?
Thinking about if it matters, that 1 is.
Yeah, I think it doesn't matter actually. And 0 maybe, 0 could, yeah, it could be, 0 could be there. And of course, this is then wrong. It should be less, not less than equal. I mean, you cannot equal infinity, so less than infinity. But it could be 0, because if this is 0, then you have really 0.5, and this is completely random, completely private. So this is fine. Epsilon of 0 is fine, completely unusable, but possible. Okay? All right, so this is it. So this is like the simple solution, just add 1, and having this formula, the theta of this function should do some job, right? Hopefully. This is what we wanted. I mean, again, we wanted to do the function that what was here? That for larger epsilons, what does it mean really? Actually, look at this graph. It's not the true one, but sort of-ish. For larger epsilons, we're getting much higher probability of reporting the true value. Yeah, what does it mean? Like less privacy. And here, if we go here to 0, well, then the probability of reporting true value versus the opposite value is going more random. And so this is more noisier. And here, this is like complete noise. Just everything is random, so no information, but complete privacy. Okay? So this is really what it shows us. Yes?
Use softmax.
So we can use softmax. This is interesting. So softmax, what is softmax?
The center point is at 0.5 and it goes till 1.
No, it's not softmax. But you're on spot, but it's not softmax. Softmax is for normalizing a vector of values to be a probability distribution where you exponentiate the stuff to make it everything kind of you use exponentiation for as an increasing function to map everything to positive numbers, and then you divide by normalize by the sum all of the values in the vector. So this is softmax. But you're referring to something where which go say it again. It's sigmoid. I think you're talking about sigmoid, not softmax. Okay. It's sigmoid. That's a spot on. So keep it for later. Sigmoid would sigmoid work here? I guess to some extent, yes, somehow, but maybe we'll see. But let's start with this simple one, okay? Because this will work. I mean, this is doing what we want. Okay. So now we have our Bernoulli trial, and then let's try to prove differential privacy. Let's try to say, well, is it private or not? Is it really protecting the bit or not, as we want with these epsilons? So for any neighboring data sets, D and D prime, which are 0 and 1, and any output privatized, which is again 0 and 1, this definition must hold, right? I mean, this is what I just wrote in the previous slide, so this must hold. And then, so let's try with our Bernoulli trial, typo, and report the true with the true value or truth, excuse me, with this probability. So this should be our function, and flip with 1 minus theta. So let's try to prove it, and let's take an extreme example where D and D prime are actually differing. So, oops, why is it 2 times here? Sorry. So let's our one data set would be 0, neighboring data set would be 1, and we're gonna report 0. So the true value of D and flipped for D prime. So we flip from 1 to 0. Okay, so what we are going to say is what's the probability that the true was 0 and we're reporting 0. So, okay, does this make sense? What we're trying to say? So if we had 0 in the database and we report 0, we parameterize with the Bernoulli distribution. What is the probability of this? That we basically report the true value, okay? And the probability of reporting true value is the theta. Right? In Bernoulli, again, oops, it's really slow here. In Bernoulli, where was that? It was we said if we end up with 1, we're going to report the true value, and this is exactly the theta. So this is the probability of success here. Okay, and in our algorithm we said if we drew 1, we're going to report the true value. Okay, so this is what we are doing here. So if we, sorry, coming back here, if we drew 1, and we're going to report the true value, so the output will be 1. Sorry, excuse me, 0. So 0 was true, and the output will be 0. So we're reporting the true value, and this is parameterized by the theta. So the probability is theta. Okay, so everybody's with me on this. Now, if the truth was 1 and we're reporting the flip value, it means that our Bernoulli trial kind of failed, and it fails with probability 1 minus 0. Okay, so everybody agrees how we get from here, what this means, and how we get here? Or any questions? Okay, cool. So let me just delete this notes. Okay. So this is basically, this is what we need to make sure that for these neighboring data sets and these outputs, this is bounded by exp of epsilon, right? Because of the definition of differential privacy, right? This was our reporting 0 given 0, and this was like reporting 0 given 1, and this to bound by this epsilon. So we need to prove this. Okay, so a little bit of, and we said that for the theta, we're going to parameterize with this kind of beautiful function. Okay, so that's what we said in the previous slide. This was our design kind of like, because it has these properties between 0.5 and 1 and maps to epsilon as we wanted. So I'm just going to plug it in here into this fraction. do some little bit of algebra. So I'm going to multiply this to make it epsilon plus 2 over epsilon plus 2. And then we're gonna, what is this is gonna be killed, you know, blah, blah, blah. I'm gonna actually change it into, well, this is algebraic operation. So you can go through and maybe double check if it's correct. So this is gonna be killed over 1 s plus, oh, okay. So we need epsilon plus 1. And now epsilon plus 1 is smaller than x of epsilon. Is it? This is a question you have to know. So let's do a visual proof. And then we can do like a formal proof. Okay, so visual proof. So what is, okay, this is epsilon. I'm not using x here, but it should be like the x-axis, right? So this is the epsilon on x-axis, and this is the values. Okay, so what is the function epsilon plus 1? Well, it's a line, right? And it goes, what's the slope of that? If we have epsilon plus 1, how does it look on the plot? Like, and so sorry, so is it going to be, what shape is going to be? It's a line, okay, it's a line. It's a linear function because there's nothing like this in the polynomial or exponentiation, whatever. So it's a line, and it's gonna be, yeah, so here, because this is 1, and then it's gonna be just a line because it's just a linear function, okay? So 0, 1, minus 1, and so on, okay? So this is epsilon plus 1. Okay, cool. What is this function? Well, let me try, okay? Yeah, this is, so it's going also through 1 because epsilon exponentiation of, so e to 0 is 1, but then it grows much more rapidly here, exponentially. And here it goes somehow like to 0 in the minus infinity. So this is x of epsilon, okay? And our visual proof is saying, yes, exponentiation of epsilon is you know, greater or equal, or it's greater except for 0 where there is equality. Okay, this is visual proof. There is another formal proof I'll show you in the slides later. But awesome! Wow, what we just did, we designed an algorithm which does this thing. So do I have this summarized? For reporting a single bit. Okay, so how does it work? Well, we have a Bernoulli distribution. We draw a random value, either 0 or 1, from the random distribution, and if this is 1, we report the true value or flip the value, and the theta is going to be this. If we use theta for this, then we design a differential private algorithm, because we just prove that this kind of bound holds for neighboring data sets. Well, we prove it, we just tried for one example, but you can try for another one, like if the d prime flipped from 0 to 1, or if both are 0 and 0. So this will hold. This will hold for all the cases for our parameterization of the Bernoulli. Okay, so you can try how many cases we will have here. It will be 8, right? So all the combinations of d prime, and output. So we have 2 values for each. So 2 times 2 times 2 is 8. And if you prove it for all 8, then you're done. That's great. The question is, we are adding some noise, right? And the noise will kind of influence the, how good the answer will be. We added some noise, and the noise should be something between 0.5 for the Bernoulli until 1. And of course, I, as somebody who's interested in the true answer, will less noise. And you, as somebody who's interested in privacy, want more noise, like more closer to epsilon, to 0.5. So, and here we say, yeah, well, we actually kind of bounded this with what we want, with what the requirements of differential privacy are. So this will work, but is it tight enough? Is it like, maybe I'm adding more noise than I really need? So maybe I can add actually a little bit less noise while still holding this bound, but it will have like better utility. So this is a good example. We kind of develop an algorithm which can, which will work. I can collect the numbers. You will protect your privacy with the given epsilon, and we'll be fine. But maybe we can do even better. So this is again like improving. Our first attempt was, okay, well, these are two neighboring data sets. This is the worst case scenario where one flipped and the other not. And we say, okay, we ended up with 1 plus epsilon, or epsilon plus 1 is still bounded by e to epsilon. And we know why. Yeah, like most of the time, the e to epsilon will be higher. And for values somewhere between, close to 0, this is fine. This is almost the same. But if epsilon grows, I'm getting much more difference between what I really need to protect and what I'm actually doing. So maybe I'm not tight enough here in this case. So the gap here is getting bigger. And maybe I want to make the gap smaller because then I have more utility because I have to add less noise. So, okay, so we approximated here x of epsilon, we approximated with 1 plus epsilon, okay, with the line, right? I mean, this holds. This is what we saw in the visual proof. I can also approximate it with a polynomial of degree 2 because this holds as well. Is it true? Does it hold? I mean, here's the answer. So don't, if you don't look at the button, then you will kind of, yeah, sure, this will hold. So, and actually this will hold even for what? Cube over 6, and it will even hold for to the power 4 of 24 plus and so on. So what is this? Yeah, or series, right? This is Taylor expansion. And this is, of course, I mean, why this holds? Because the very definition of this function, one of them is the Taylor expansion, which is 1 plus x squared over 2 plus x cubed over 3 plus x4 over 6. Oh, sorry, no, 6 here, 24, x5, and I don't know the factors of that. But this is the very definition. And now, of course, if you remove a couple of these terms, this will be turned into inequality. So you can approximate this with this polynomial. So here we see we had a line. But if we had a polynomial, this would still hold, but will be tighter. So still holding the privacy guarantees, but maybe we need less noise. Because why? Because the amount of noise, the amount of keeping the true value would be higher. And this is what we want. We want to keep the true value as much as possible. Somewhere here is the bound. So this is the bound of x of epsilon. I mean, 1 minus, I guess. And it's more complicated. It doesn't matter. But there is a bound I cannot cross. But I want to be as tight as the bound as possible because I want you to give me the truth. If this were like that, yeah, then the utility is bad. I mean, it's, yeah, the bound still holds, but you're really more reporting the more random stuff, even for large epsilons. Yeah, this is good for you. The privacy will be still intact because you're still bounded by this e to epsilon. But I want actually, for utility, I want to be this as close as possible to this bound. And actually, we can turn this inequality into equality. And that's really on the next slide. So again, our first attempt was, okay, let's parameterize with this theta, which is this thing, and this gives us a line approximation, which is still bounded by, by the guarantees. Cool. Now, what if we replace this part with not an approximation, but actual thing, like this would turn into basically this, and let's try to work it backwards to find what the theta will be, because we want the theta to hold, this inequality, but maybe there is something where I just say, yeah, well, I don't have to approximate this. I just use the actual same function, and then what could be the thetas that this will be true. Okay, does it make sense? Like I'm trying to be better than this. I mean, I could try, as we saw here. So this will also hold. So I can try to plug in a polynomial. So for example, here plus epsilon squared 2, and this will still hold. And then I would kind of need to find out what these things were. They will be different. Yes?
Just sigmoid without negative number?
Let's see. It might be. But I just really want to do like backwards, like step by step, okay? If I tell you it's a sigmoid, then yeah, of course, everything is clear. But why is it so? Because I want to be as close as possible in this bound. So I'm replacing this with equality. So this was the first attempt again. What we did, we had this theta epsilon plus 1 over epsilon plus 2. And I'm just like rewriting here with 2 is 1 plus 1 to make it very explicit. So this was the first kind of proof of the naive mechanism we did 5 slides back. Okay, so now, and I'm gonna here exchange it with exp and just work this out backwards in a way. And I'm basically replacing epsilon plus 1 with this exponentiation. So here, this will be replaced, and this will be replaced, and this will be replaced. Okay, so I get this. Okay, nice, got it. Then I'm coming back. Yeah, so I replace these things, and these things. So I'm getting this kind of thing. And back then, yeah, okay. So this will turn out nicely. Okay, I got a beautiful kind of thing. So if I had an idea like at the beginning, as you had, like maybe sigmoid, well, okay, sure, I would say, sigmoid, and let's go. But now I'm taking like, well, it doesn't have to be sigmoid, it could be anything else, we just fulfills the criteria. But sigmoid actually turns this into equality. Yeah, but it's still hold the bound. This is it. We are as close as we can be. I mean, we are the tightest kind of privacy guarantees by using not some sort of function here, but by using actually sigmoid, which is exactly on the bound of the privacy. So this is why it's, why it can't be any tighter. So let me just come back. So, okay, so for everybody knows what a sigmoid is. If you don't know what is a sigmoid, this is your friend, sigmoid function, sigmoid. And we use it in machine learning and NLP and everywhere as a kind of projecting any real number into a probability value. So, and it looks something like that. There is this beautiful knee, and then it saturates to 1. Okay, so this is a sigmoid of X. And there's 2 forms I'll show on the next slide. But this is basically how we end up with the sigmoid here in the, by working backwards this bound. So what could be the tightest bound? Yeah, well, like that. And we took inspiration from our kind of naive attempt. I guess this is the way how people kind of discovered this thing. Maybe not. Maybe they're just like, let's do like sigmoid, maybe. But does it make sense? Why we end up here? Because we want the tighter bound, as tight as possible, because still protecting privacy, but most utility, less noise. Okay, so we found the tightest theta, and the theta is the sigmoid, and actually this still holds, and the inequality still holds, but it's actually equality for some cases. For some neighboring data sets like 0, 0, 0, 0, this will be 1, and 1 is still less than x of epsilon for any values, so this will hold as well. So recap our algorithm. So what we do, we draw a random value, either 0 or 1, from a Bernoulli distribution. The Bernoulli distribution is parameterized by this sigmoid. But it's a coincidence. It's a a coincidence. It doesn't have to do anything with probability mapping to probability or things like that. I think it's more like a coincidence with this bound of differential privacy, which is e to epsilon, and this Bernoulli. So we have this random value drawn, and then it's parameterized by this. I mean, this is also like sigmoid. Most people use this 1 over e2 minus epsilon. Why? Because you don't have to compute it twice, this value, and whatever. And if this is 1, we report the true value. If this is 0, we report the flip value. And this makes our algorithm epsilon 0 differential private. Nice. So now we can use this algorithm. I can ask you, the bit question, like I don't know, have you cheated in an exam? How are you gonna do that? I mean, you draw a random value using this. We have to agree on epsilon first, and then you do the draw from Laplace, excuse me, from the Bernoulli, and either give me the truth or false. How can I reconstruct the true value? I don't have it in the slides here. Maybe we do next time or in the exercise. It's some like averaging and subtracting some stuff, like getting rid of the noise and trying to get a mean value. And what we just did today, we rediscovered the randomized response algorithm. So we kind of did it really from, we invented the randomized response algorithm. And I would say, well, we have this proof already, but maybe as a homework, just prove that this randomized response is really epsilon 0 dp. So we just did it for one pair of d prime, and y, but you can do it for all of 8 of them. It's a very simple proof. I mean, basically this, but with different d and d primes, okay, and y's. Just do it and make sure then, well, for all of them, this will be either equality or inequality. Either will hold. Okay, so that's what we did. And why is it good? Okay, so this is interesting. We move to the local differential privacy, which means there is no trusted curator needed. Okay, so I can ask you and you and you. You have database of size 1. This is kind of like a step in thinking about differential privacy. Well, you want to learn statistics about population. So if you give me one value, I learn pretty much nothing because there is a lot of noise, right? I mean, the noise is kind of proportional to this Bernoulli. But if I collect it from more people, then the estimate of the true kind of mean is getting better, like kind of less noisy. The error is getting smaller in that. So why is it important for privacy preserving NLP? Where is NLP again? Well, the thing is now, okay, now we know how to privatize a bit, and you can give it to me, and you have a plausible deniability. So I don't know what your true value was. You can always say, yeah, the chance kind of made me to flip my coin, so I didn't cheat or I cheated. There's an example we can do this randomized response with a coin tossing. But we're not gonna do it today. So basically you would toss a coin. If it comes heads, you will tell me the truth. If it comes tails, you will toss again, and then depending on the second outcome, you will tell me the outcome of the second one, so some random value. And it will give you randomized response with epsilon of 1.1, logarithm 3. We can do it maybe on exercise, or maybe next time just about thinking about the utility. It's kind of fun exercise. But the thing is, we can use it for privatized raw data and publish. So, I mean, of course, nobody's in NLP, we're not interested in one single bit. But you can extend it, like one single bit, you can extend it to vector of bits. And with a vector of bits, you can privatize more than just one bit. You can privatize the number of bits, which can actually encode a message or something like, you can encode stuff in a bit vector, and you can privatize it and publish. And then I can use it maybe for training machine learning models. So for example, what could that be? It could be, oh, okay, interesting. So for training, what is one-hot encoding?
There's like a bunch of data for example, you have like weather, good, bad, rainy, and you can encode that into a vector where we have like a bool for each of them.
Okay, so you have exactly. So you have 4 categories, you say, and you would say first category is the first bit position, second category is second, and this would be like 0, 1, 0, 0 if the second position. Okay, so you would consider it for labels if you have like multi-class. How about doing this for back of words? Can you do it with back? What is back of words? Back of words, you have a vocabulary, let's say 10K, or make it smaller, like 100 words, like top 100 words. And then you would say, well, if I have a text and the word is present in there, I just put 1. Not the number of occurrences, but just the presence of the word. And if the word is not there, I get 0. So basically, you would turn your text into a vector, a binary vector, whether or not the word from the vocabulary at this position is present or not in this vector. It sounds bad, actually, like, is it any good? Because you're throwing everything back of words and there's not even like counts of these words, but you'd be surprised for some tasks like sentiment analysis, it would work kind of okay-ish. Oh, this is interesting. So now you can turn a task of, let's say, sentiment analysis into a vector of bits. Now, theoretically, you can privatize this vector of bits and just give it away. And I can use it for training machine learning model without violating your privacy, whatever was in the text, for example, which words you use, because each bit position will be privatized using this randomized response. The big question now is like, how large the epsilon has to be overall that it has any value for me, and also how many data points I need to collect in order to train something like not completely noise. And that's something not to be covered today. But theoretically, this is a mechanism people are using with more or less success. So, and the point is also randomized response, what we just developed here. It's known from the 1965 by an author called, I think, Stephen Werner, 1965. And they use it actually since then for asking people like, do you take, have you committed any crime? Well, of course, you're not going to tell me, it's even worse than cheating, but I'm really interested in population. So you would use randomized response and report back the privatized value. So you can always tell me, no, it wasn't me. It was just the coin, the randomness in the process. So you have the plausible deniability again, but each and everybody. Overall, over population, I'm going to find out like how many people actually taking drugs or committed crime or cheated in the exam. Okay, so I guess we covered pretty much everything today. Any questions? Sounds great. So let me stop recording. And I hope I recorded it, to be honest.